All right, great. So it is my pleasure to introduce Caroline Lemieux for our Tech Talk today. Starting the summer, Caroline's going to be an assistant professor in the Software Practices Lab at the University of British Columbia. And she received her PhD from UC Berkeley, and right now is a postdoc at Microsoft Research in New York. Her research focuses on techniques for improving the quality of software, ranging from fuzzing, which I'm sure we'll hear a lot about today, to specification mining and program synthesis. And in addition to her academic projects, she's worked with research groups at Google and Microsoft on developing tooling to actually use these techniques to find real bugs and security vulnerabilities in their systems. I'm really excited that Gawa is going to have the opportunity to work with her on an upcoming DARPA research program, where we're going to explore the use of fuzzing and synthesis techniques to understand and mitigate sources of exploitability in programs. But today, Caroline's going to share with us some of her work on expanding the reach of fuzzing techniques. I hope everyone is as excited to hear about that as me. So take it away.
Thank you so much for that kind introduction, Scott. So before I get into expanding the reach of fuzzing, let's just set the stage on what motivates me in my research, right? So I think we know that humans continue to err as they write software, and so software still has bugs, right? And as software becomes increasingly pervasive throughout all different aspects of our lives, these bugs can have increasingly severe consequences. For instance, in the last few years, we've seen a number of pretty important security vulnerabilities emerge from just basic correctness bugs in C and C++ programs. And even beyond the bugs that, get the celebrity treatment of having logos and news stories written about them, we know that behind the scenes, the cost of bugs is quite severe. One estimate from the Consortium of Internet Software Quality estimates that the cost of poor quality software was nearly $2.8 trillion in the US alone in 2018 alone, right? And US is not the only country in the world, so we can assume that this cost is quite large overall. So in light of all this, in my research, I aim to build tools that help developers improve the correctness, security, and performance of software. And in this talk today, I'm mostly going to focus on one set of these tools, whose goal is to automatically find bug-inducing or other kinds of interesting inputs in software. So I'll start by giving you a bit of background on fuzzing, or fuzz testing as it's known. Then I'll talk a bit about my work in expanding the reach of fuzzing, and if we have time, I'll allude to some future directions. In terms of my work on expanding the reach of fuzzing, I'll talk about kind of three main categories in which I've generalized existing fuzzing algorithms to bring fuzzing to new application domains. First of all, I'll talk about Perfus and Fuzz Factory, where by changing the notion of feedback that we had in the fuzzing process, we were able to effectively find performance bugs or inputs that show interesting performance behaviors in programs. And then I'll talk about Fairfuzz and Zest, where we'll see how by mutating inputs in a more smart manner, we were able to better explore the core logic of program rather than just parsers. And then finally, I'll talk about some kind of more exploratory projects, RLCheck and Autopandas, where we used some of the ideas from generator-based fuzzing, but plugged those in with kind of smart backends to achieve new goals, including some forms of program synthesis. So with all that being said, I'll start by giving you a bit of background on fuzzing, and I'll try to stop after each of these sections if there are any questions, but feel free to put any clarification questions in the chat or interrupt me as well. So first of all, what is fuzzing in this context? So the term fuzzing dates back to this 1990 Communications of the ACM article from Barton Miller and others, where they found that if you take a bunch of popular Unix utilities and you send to them just random sequences of just random garbage characters, eventually one of these sequences of random characters would cause these actually kind of popular Unix utilities to crash. And they called that program, which was generating these random sequences of characters as input, the fuzz program. And it is this paper that thus birthed the term fuzz testing in terms of just sending random inputs to programs under test. Now, modern fuzzing keeps some of these flavors of randomized input generation, but it's gotten somewhat more complex. We've seen it be adopted across all different types of industry and open source. And these modern fuzzing techniques have been really effective at finding bugs in large-scale software, including ones that you use every day. Here are some maybe slightly outdated bug trophy cases from some of the most popular coverage-guided fuzz testers, which is one brand of these modern fuzzers. But I think to really give you an idea of the impact these tools have had, we can look at one of the kind of shining case studies of the success of these tools, which starts with a less shining case study in the success of finding bugs. If you've been around for a while, you might remember the discussion around this Heartbleed bug in 2014, which was a bug in OpenSSL, which is a library that undergirded at the time most HTTPS communication on the internet. And there was a buffer overrun, which essentially had a bunch of large costs. In Canada, it shut down our revenue agency's website. In the US, it led to millions of hospital patient records being compromised. And part of the reason I posit that it had such severe costs was because although it was introduced into OpenSSL in 2012, it was only discovered and fixed by the maintainers nearly 2 years later. It was discovered by some external security auditors and then fixed. So in those 2 years, there was quite a bit of chance for this bug to spread and become exploitable. Now, on the other hand, 2 years after Heartbleed was discovered, there was another bug discovered in OpenSSL, which was actually judged to be much more potentially critical than Heartbleed because it could lead to arbitrary code execution. But you've probably never heard of CVE 2016-6309, unless you're really into fuzzers, because it was only discovered one day after its introduction by one of these modern coverage guide fuzzers. So it didn't really spread as widely and become exploitable like Heartbleed did. So what are these modern fuzzers that are able to find these bugs in complex software systems? They're not quite as simple as just sending random inputs to programs under test. The coverage-guided fuzzer that found that critical bug in OpenSSL, HongFuzz, is in this lineage of coverage-guided fuzzers, which was really pioneered by AFL. And the way that most of these fuzzers work is that they start by not from just pure randomness, but from some set of reasonable inputs to the program under test. And then they pick one of those inputs to mutate, and they generate new inputs by mutating that picked input in a very naive byte level manner. So here we've, say, duplicated a random byte in this XML document. And then the really key kind of coverage guided part of this loop is that we've instrumented the program under test so that when we execute it, we get information about what happened when the program under test was executed on some inputs. In particular, for each input, we keep track of the branch coverage in the program under test, right? Essentially, which true false sides of if statements were covered by each input, right? So for each input, we see the different branches that it covered. And then we close this whole feedback, this whole input generation loop by looking at that coverage, assessing which inputs had new branches covered, i.e. which inputs had new interesting behavior, and saving those inputs to this set of seed inputs so that they can then be mutated again, and so on and so forth. And through time, you see that this set of saved inputs is going to cover a larger and larger variety of program behaviors. So that's coverage-guided fuzzing in a nutshell. Beyond AFL, libfuzzer, and HongFuzz, there's been a lot of works into improving this in academia, including, say, AFL Fast, which was kind of the seminal work bringing in the discussion about the AFL algorithm into the academic setting. I would say the other big bucket of modern fuzzers that are not really coverage-guided tend to be what I would call generator-based fuzzers. So in a generator-based fuzzer, the picture looks a lot more like random fuzzing from CACM in 1990. But instead of generating totally random sequences of bytes as inputs, we have this input generator, which is a non-deterministic function, which each time it is called returns a random input, but in a given search space. So as an example, say we're testing an XML linting program, we might write this simple XML generator that each time we call it returns a different random input. But all of these inputs were, say, well-structured XML documents. So accordingly, we're going to explore really different parts of this XML linting program than we would if we were just sending it random sequence of characters. And now, one of the big catches with generator-based fuzzing is that typically this generator or the grammar that's used to derive the generator is going to have to be written by a developer conducting testing, unless they can reuse a suitable one because they're using a really popular input format. And under this umbrella of generator-based fuzzing, I'm lumping a lot of different things, including quick check, which is kind of more property-based testing, which is like fuzzing at the unit test level with typed inputs. But you could also consider things like CSmith, which is a tester of C compilers as a really highly specialized generator-based fuzzing, where you have this generator that's highly specialized to generating C programs that don't have undefined behavior. But they all kind of follow the same concept of having a generator that generates inputs in a given search space. So in spite of the successes I alluded to of all these techniques, of course, as I'm giving the talk, you'll imagine that I'm going to say there's some drawbacks we can address here. And there are a few of those. So first of all, in coverage-guided fuzzing, traditionally, you kind of just had this fixed testing goal of increasing branch or edge coverage of the program under test. And depending on what kind of inputs you want to generate, this might not actually always be the search goal you want. And we'll look at different ways that we can alter that search goal to, say, find performance bugs in the first part of this talk. And then there's kind of a double-edged sword in the way that we generate inputs with coverage-guided fuzzing, which is via random mutation. So random mutations are great because we don't need to specify any input structure or anything, but they result in a lot of malformed inputs, which can prevent us from testing the program very deeply. And we'll look at ways to make those mutations more structured in order to explore more core logic of the program in the second part of this talk. And finally, even though generator-based fuzzing is great, if you sit down and write a good generator for your program, sometimes doing that is quite difficult. And it might be not difficult, but it might also be difficult to get right as a developer. Like, what exactly are the inputs that my program is expecting? So in the last part of the talk, we'll look at some ways to kind of separate, to remove some of the user work and tune generators automatically to different testing or search goals. So with all that being said, unless there are any questions, I'll move on to the first part of the three middle parts.
I have a slightly non-technical question. I was curious in the OpenSSL CVE example. So that was found really fast. Do you know, like, was that found by people associated with OpenSSL, or is this some independent person who, they set up a fuzzing campaign and they just do this on every release? I don't remember who was running. I don't remember, but this is on this is really prominent on Hong Fuzz's trophy case. They're like, we found the only critical vulnerability in OpenSSL. It might have been the folks that were continuously fuzz. Like, I know at Google, right, they continuously fuzz a lot of open source projects. I don't know if it was them or someone else. Yeah. And there's a question in the chat for you, which is, how do you track internal branching in code logic without modifying the source?
Yeah, okay, so that's that depends on the fuzzing tool, but essentially, depending on whether you're using libfuzzer or traditional AFL will inject, you essentially inject a compilation. You have a compilation patch which injects tracking for every edge in the control flow graph when you hit it. So it's at you don't modify the source, but you intercept the compilation, and you look through, you essentially have some logic to like keep track of the start and end of different jumps in the program, and you map that to some edges. So you do it at compilation time. Yeah, there's a question about quick check.
Yes, you had mentioned that it came under the class of these generator-based testers that were the developers writing the generator. But in quick check, that's partly automatic, right? It's based on the type of the inputs. So it uses the data type to automatically enumerate things within, so you don't have to worry about the well-formedness, for example, of the input.
Yeah, for sure. So in quick check, if your type of your argument encodes all the validity constraints, like if your function is, every binary tree is an okay input to this function, then, and you're in a functional language like Haskell, where, everything is generated in a nice manner, then you can get generators automatically from types. The story gets more complicated if the type is not the only thing that a valid input, like if it's not the only constraint on a valid input. It also gets more complicated in languages like in C++ or something, where you might have factories that generate objects, or Java, where you have object creation factories or different ways of creating inputs. So you might not be able to derive a good generator all alone from the types. Yeah, that's a good question. All right. So that's the high level on fuzzing. Let me talk a bit about these Perfus and Fuzz Factory projects, where the goal is to adjust fuzzing and the search to finding different kinds of bugs. In particular, we were curious about this problem of performance bugs, right? Where on most inputs, your program is performing fine, but there are some inputs on which the program blows up in terms of runtime or memory usage. And these can range from annoying, like this input that causes a compiler to take over a minute to report a syntax error, or they can be another source of vulnerabilities. For instance, this CVE in 2020 was found in Python's URL library, where they had some unexpectedly quadratic behavior that could potentially cause a denial of service attack. So we were interested in whether we could use these kind of modern fuzzing algorithms to find performance bugs automatically. And you might think of one way of doing this, which is to look at this coverage-guided fuzzing loop and say, why does this need to only be guided by coverage? Couldn't I just keep track of the execution time of inputs and then save inputs that execute for longer? And then eventually I'll find any performance problems in my program. Well, it turns out that if you try to do fuzzing where you're really just trying to maximize a single objective, like I'm going to keep track of the execution time or just the path length of inputs through my program, you'll have a tendency to kind of get stuck in local maxima as your programs get more complex, because you're no longer exploring enough diverse behaviors. So I'll go through an example of how we managed to get around this problem in our tool. And in particular of what are we going to do if we're not just maximizing path length or runtime. So to look at this, I'm going to have kind of a detailed look at this word frequency program, which essentially takes as input a sentence and outputs the number of times each word in that sentence appears. And the reason we're looking at this is because a version of word frequency that shipped with Fedora Linux had a performance problem. Its worst case was quadratic because it was implemented as a linked list hash table. And linked list hash tables are quadratic in the worst case if you have all hash collisions. So on the right-hand side here, I have kind of an approximate control flow graph for the core function of this word frequency program implemented as a hash table. And to see how we could automatically find inputs, finding the worst case behavior, we're going to look at the performance response of this program on different inputs at a more granular level. And what we're going to do is we're going to look at the number of times each edge in this control flow graph is hit, right? And edge is kind of similar to an edge includes the branches in the programs as well. And for the purposes of exposition, I'm not going to count the hit counts of every branch of every edge in this control flow graph, just the ones I've labeled A, B, C, D. So for a usual case input, like the quick brown the dog, there are 4 unique words. So the A edge corresponding to creating a new entry in the hash table is going to get hit 4 times. There is one word that has the same hash code as an existing word. That's the. So the B edge is going to be hit. But since the is actually identical to the word it has the same hash as, we're only going to hit the D edge corresponding to incrementing the count in the hash table. Now, this map of edges to hit counts would look very different if we pretended that this input was actually pathological in the sense that all the words in this input had the same hash code. They don't, but let's just pretend they do. Let's pretend the math works out. And in that case, right, we would see a much larger number of hit counts to these B and the C edges that correspond to traversing the linked list. On the other hand, the A edge isn't really executed that many more times than the usual case. And what if for some reason it was really expensive to create new entries in our program? We might want to know, is there an input that causes unusually high creations of new entries? And in this case, the result is not really surprising. The input that maximizes the hit counts to the A edge is just one that has a lot of small unique words. There's no unexpected quadratic behavior or anything here, but that's kind of the worst case for the hit counts to the A edge. And what I want to highlight here is that the pathological performance behavior of these inputs is really characterized by hit counts to a few control flow graph edges, right? So the first time I create a hash collision by mutating an input, it might not actually result in a much longer path through the program than say, or a larger runtime than say, if I have an input that has a lot of small words. But it will cause the B or the C edge to be executed more than I've seen in an input that has a lot of small words. So the idea of how we can get around this problem of getting stuck in kind of local maxima and not finding worst case or different performance behaviors is that we're going to try to maximize each hit count of control flow graph edges in our programs independently. So that's exactly how we modified Coverageguided fuzzing in Perfus. So instead of just keeping track of the branch coverage, we keep track of a detailed number of hit counts for each edge in the control flow graph. And then we save inputs, which maximize the hit count for some edge. And we pick inputs for mutation if they maximize the hit counts for some edge. So this allows us to make some sort of progress, right? So if you're the one that has the highest hit count of A, the A edge will choose you for mutation more often. And when we ran this compared to state of the art at the time, we found that Perfus was better able to find true worst cases than when you had a single objective. So slow fuzz was one of the first tools that was proposed to find these kind of worst case algorithmic complexity issues in programs. And it was just trying to maximize the total path length through the program under test and do some fancy stuff with mutations. But kind of the worst case inputs it would generate all looked like this, which you'll recognize they have a lot of small words in them. On the other hand, when we ran Perfus, we found that the inputs it generated had this kind of strange structure. And they all had this weird structure with weird unprintable characters. And when I analyzed these more carefully, I realized that all the inputs Perfus were generating were exactly showing kind of the worst case performance behavior of this program. They were inserting a small character into the linked list hash table, a small word. And then they were inserting a bunch of other words that had the same hash code as that word, and then forcing the insertion of that small word over and over again at the end. So you had to traverse this linked list a bunch of times. Right, so we were able to automatically find these inputs in this program. And this even scales as programs get a lot larger. So that compiler issue I mentioned earlier, we found that input automatically using perfuzz that caused, the one we found automatically took 1.5 seconds to report a syntax error, but you could straightforwardly extend it to find it to the pattern that would cause, it to take over a minute to execute. And the cool thing about Perfus is that beyond the fact that we could find these algorithmic complexity issues with this edge and hit count maximization, actually in the paper, and as we were thinking about it, we were thinking that it should work more generally, in that this algorithm should actually work, not just for maximizing hit counts of control flow graph edges, but for any kind of search objective that you can pose as, I want to maximize values for some keys. And in Fuzz Factory, we created a framework that allows us to more easily express those objectives. So for an instance of what's something you could do with this generalized fuzzing algorithm, say you want to find out of memory bugs. Well, what you could do is keep track of all the memory allocation locations in the program. And then for each of as keys, and then as values for each of those keys, just keep track of the cumulative amount of memory allocated. And you can do this. And let's say we'll build a fuzzer that is just trying to maximize memory allocations in that manner. And let's compare it to regular coverage-guided fuzzing. So regular coverage-guided fuzzing is in the blue. The memory maximizing fuzzer is the orange striped lines here. And on the y-axis, we have the maximum memory allocated by an input generated by the fuzzer. And it's like, okay, or generally the orange striped bars are higher than the blue bars. Seems like it works. But you'll notice that on one of the benchmarks we were looking at, actually we had smaller memory allocations with this memory maximizing fuzzer than with regular coverage guided fuzzing, which was strange. So we looked at this benchmark more carefully and we realized that it's libarchive, it's, I guess it's unzipping. And in it, there were a lot of these hard comparisons where essentially a subsequence or a function of the input X was compared to an exact value. And if you're just trying to maximize memory allocations, you're not necessarily making much progress getting through these hard comparisons. But actually, getting through hard comparisons is another problem that we can pose as this key value maximization things, right? If we keep track of keys, all the hard comparison locations in their programs, by which I mean these strict equality comparisons. And then as value, we add this compiler pass that keeps track of the numbers of bits that match between the left and the right of these hard comparisons. Well, now if we have a fuzzer that tries to maximize the numbers of bits matched for each of these hard comparisons, we're eventually going to generate inputs that flip the branch. And what Fuzz Factory actually allowed us to do in addition to Perfus is it allows you to easily compose these objectives. So you can just say, I want a fuzzer that both tries to maximize memory allocations and tries to get through these hard comparisons. And I'm showing you the results on this graph. So this graph actually still has those blue and those orange bars, but they're so small you can't see them. And the dotted green bars are the fuzzer that's just trying to get through hard comparisons. And then the yellow bars that are the highest here are the fuzzer that composes these two objectives of getting through hard comparisons and increasing memory allocations. And it's that, super composed fuzzer that was able to consistently find these memory allocation issues in programs, including in libarchive. We found this LZ4 bomb, which is quite impressive because libarchive had been really extensively fuzzed by regular coverage guided fuzzing, and it on its own couldn't find this type of behavior. As a side math note here, another neat thing about Fuzz Factory is we actually generalized this further and figured out that coverage guide fuzzing is a sub-instance of this kind of search algorithm. So in Fuzz Factory, actually you can make this work for not just maximizations, but some other forms of aggregating values, as long as that aggregation satisfies idempotence and some associativity properties. And you can capture the coverage guided fuzzing algorithm itself as an instance of this algorithm. So the big takeaway from both of these works is that if we want, by generalizing the notion of feedback in these fuzz testing algorithms with this map-based abstraction, rather than just considering branch coverage, we were able to target new different bug domains. So yeah, so if there are any questions at this point, I can take them. All right. I think I left you 10 seconds.
I'm sorry, I actually do have a question.
Okay, go ahead, yes.
Is it the case that coverage-guided fuzzing, like traditional mutational coverage-guided fuzzing, could be recovered from Fuzz Factory if you took like the number of hit counts of CFG edges as your metric?
Yeah. So you can recover coverage guide fuzzing. Essentially, coverage guide fuzzing, it doesn't just look at whether new branches are executed. It looks at whether they're executed in certain buckets, like one. Anyway, so you can essentially have instead of looking at maximizing values, you can take set union. So you can say like this branch was covered 1, 2, 4, 18 times, and you can recover coverage guide fuzzing as an instance of Fuzz Factory.
Can I ask one more question, which is,
yeah.
How much do you rely on information from the compiler? Like, for example, the control flow graph is one example that you might have mentioned here. What all things do you expect or would like to have from the compiler for this?
Yeah, so that's a good question. So for like Fuzz Factory itself, the interface it provides is like an interface that relies on Clang compiler passes. So the information we use is being able to we use the ability of being able to traverse functions and find edges in the control flow graph. You don't need a compiler to do the kind of regular coverage guide fuzzing. There are ways of doing this in a binary only manner. And there might be ways of implementing Fuzz Factory in a binary only manner, but we haven't done that. So we rely on compiler passes to insert calls into that create this feedback map. But that's mainly what we get out of it.
And what about?
But given that you rely on something from the compiler, is there a wish list of what you would like from the compiler?
I don't have one off the top of my head. Like the Clang like compiler passes treat us pretty well. But if something jumps to my head later, I'll let you know.
What about cases where you've got a virtual machine like Java?
Java, we have another way of getting the instrumentation in Java. I'm not like an expert in how we get the instrumentation out, but I think we do analysis at the bytecode level.
Okay.
I'm happy to look into more of that and talk about it offline, but I don't have all the implementation details off the top of my head. Yeah.
Can you hear us?
Yep.
I was wondering, can you say a little bit about how do you do this maximization step? I mean, obviously because like for coverage, it's kind of obvious. You just try to change the Booleans to kind of go one way or another. Mm-hmm. It seems quite a bit more complicated if you just have some tables. How do you map that into generating kind of inputs that will maximize those things?
Yeah, so the way you do it is that you essentially rely on the assumption that an input that has a high value, the input that right now in your mutatable space has the highest value for some key. You're relying, all of this, including coverage guide fuzzing, relies on this assumption that if you mutate that input slightly, you might be more likely to create other inputs that increase the hit counts of that key. I don't know if that makes sense, but it's...
So you try to tweak it a little bit and then evaluate it again based on these metrics and see what happens, kind of?
Correct, yeah. So you're not doing any targeted you're not like targeting mutations themselves. You're focusing on the fact that, well, this input increased the hit counts of this edge. So maybe if we mutate this input slightly, it'll increase the hit counts of this edge. We evaluate the mutants. If we find one that increased the hit counts of this edge, great, we save it and we continue making progress.
Okay,
yeah.
Thank you.
I'm going to move on to the second set of works here, which gets a bit into what I've been discussing here about mutations and actually into fuzzing Java, although my slides don't really mention the fact that we're fuzzing Java. But to do that, I'll start by talking to you about these FairFuzz and Zest projects. So if you look at a lot of the programs that we tend to test with fuzzers, they kind of have two different stages. First, an input validation stage where you check whether the input is valid according to some things you have. And then you actually execute the core logic of the programs. Like say if you were fuzz testing a compiler, then your input validation stage might be, the syntax checking, while the core logic of the compiler might actually be, generating the assembly code, doing the optimization, all this, so on and so forth. Now, the thing is that with these coverage-guided fuzzers, even though they find real bugs in real software, a lot of the bugs they find tend to be in this input validation stage. And I mean, that's good because there are bugs in the input validation stage. But why is this? Well, the real reason this is happening is because of the way we generate new inputs, which is via these random mutations, right? So these mutations are quite naive. They're just flipping random bytes, adding random bytes somewhere. They're kind of specialized to binary file formats, but they don't know a lot about the structure of inputs, which means that, say, even if you had a well-formed XML document, if you're mutating with default with one of these AFL or libfuzzer tools, you'd end up with a bunch of inputs that are no longer well-formed XML because the mutators are not aware of the structure of the input. So in the first project I'm going to talk about, I was trying to figure out whether you could answer this question of, can we figure out a way to retain the important structure of inputs without requiring additional information from the user? And in FairFuzz, I address this via this branch mask idea. So essentially the idea is that in FairFuzz, we identify some target branches, which hopefully cover core logic of the program. Like say that this is a target, the true side of this branch is if the tags match in my XML fuzz input. The way we identify that in FairFuzz is via a heuristic that we look at which branches are rarely executed by fuzzer generated inputs, right? You can imagine if my fuzzer ruins the structure of inputs most of the time, then the branches that require having well-structured inputs are probably executed less often. But we do assume that that rare branch that we're targeting has been hit by at least one fuzzer generated input, and we find such an input. And then we calculate this branch mask for it, which tells us where we can mutate the input and still hit the rare branch. And then when we generate mutants later on, we mutate it only at the locations that are allowed with the branch mask, which say are the EZ locations here. And then hopefully those inputs have a much higher chance of hitting that target branch than you would if you had just mutated all possible positions in the input. So that's how the branch mask is used. But I think the lingering question that stays here is, how are you going to generate this branch mask in the first place? And that is a great question. And and in FairFuzz, the way that we did that was via this kind of approximate computation that we perform at fuzz testing time. So essentially the idea is we're going to hijack some of the mutations that were performed by AFL. In particular, we're going to look at when we mutate the input, we go through all positions of the input. We mutate the first byte and we see whether the mutant that mutated the first byte of the input under test, whether it still hits that rare branch. In this case, it does not. So we mark that position as not okay to mutate. We keep going. If we flip the second position, do we hit the rare branch? We don't. We mark it as not okay to mutate. We keep going with this for all the different parts, all the different positions of the input until we get some positions which are marked as okay to mutate because the mutants still hit the rare branch. And for here, we find that those E and Z characters, you can still hit the rare branch. And you keep doing this for every position in the input. And in the end, you now have for each position, like a test of was it able to hit the rare branch or not? And you can summarize, that's the information you summarize into this branch mask. So essentially this branch mask says, under this test I did of trying to generate one input, then generate one input that mutated this position, were we still able to hit the rare branch? Okay, so this is a kind of a approximation to the perfect branch mask you could have. And then the way that we modified Perfus was the following. Again, we modify the way that we pick inputs for mutation, in that we pick inputs that hit rare branches to mutate. And then at mutation time, we compute this branch mask, right, by mutating every position in the input. And then further mutants we create only by touching the positions that were allowed by the branch mask. And what I found by the time, these graphs show branch coverage achieved through a 24-hour time frame for Perfus and some other state-of-the-art fuzzers back in 2018. And what this shows is that Perfus was able to achieve up to 10% higher branch coverage on some benchmarks, and essentially usually achieve the same coverage on the other benchmarks. And the ones on which it achieved kind of up to 10% higher branch coverage, when I looked at them manually, it turns out they were benchmarks with highly nested structure. So like lots of if statements within if statements, right? You can imagine that then this masking procedure is going to help you explore the program more deeply. And Perfus has also seen continued use in the fuzzing community. Folks have asked about its integration into the state-of-the-art AFL++, and have mentioned that, in part of best practices, when you're launching a fuzzing workflow, you should probably include one of your parallel fuzzers be Perfus, because it has this very different kind of depth-first exploration compared to other fuzzing techniques. Now, in spite of the, kind of adoption of Perfus in part of the fuzzing community, I was still wondering whether we could do better than this in terms of getting higher level mutations if we had more information about the input structure, right? Like, could we do better mutating XMLs than just masking out the tags if we had more information about what an XML document looked like? And this is where I'm bringing back, the idea of input generators. And right, because input generators, just a imperative program that generates a random input in search space. We see those emerge in a lot of, kind of naturally in a lot of software testing. But an input generator, it's a program that when I run it, returns a random input. How am I going to use that in my Coverageguided fuzzing loop where I'm trying to mutate inputs? Well, the key insight is the following, right? That, well, really a generator is kind of like a parser from a source of randomness to an input, right? So my source of randomness gives me the random string foo. I use that as a tag for the root node of my XML document. Then my source of randomness gives me the integer 2. I use that to generate 2 children to this XML document. And I'm going to recursively call this generator to generate those children. And then here my source of randomness might give me the Boolean false. And I decide not to generate any text for the root node, although you see that for the BAS node, the source of randomness gave me the Boolean true, and I generated some text. And the thing about how a lot of these source of randomness are implemented is that, well, in the end, they rely on this infinite sequence of random numbers, or really an infinite sequence of random bits. And that infinite sequence of random numbers is being manipulated by the choice operator, by the next int operator, by the next Boolean operator to return higher level type values, right? So for instance, to generate a Boolean value, you might ask for a random byte and then, take it modulo 2, true or false. And the thing is, if you just mutate that infinite random, pseudo-random bit sequence, you'll end up getting a structured mutation on the input. So if you say mutate these bytes, these bits in this manner, your random.choice operator is going to return the tag woo instead of foo. But because it's still returning a valid element of tags, which it always will, because it's just using those random value, that infinite bit sequence to guide which value it generates, it's still resulting in an execution of the generator that's still generating an XML document because we wrote it correctly. If you don't write it correctly, then obviously you're going to have some issues. But if your generator only generates XML documents, whatever sequence of infinite random numbers you give it, it's always going to output an XML document. So now if you just view generator-based fuzzing as going not from randomness, but from this notion of random parameters to generating an input, you can see how you can paste it into this coverage-guided fuzzing loop. And that's essentially you mutate the parameters instead of the input. And then you get higher level mutations in through the generator. And I see there's a hand raised, so I can take that question now.
Hi, yes. So have you thought at all about approaches like probabilistic programming and Gibbs sampling and all that kind of stuff to think about, could you use properties of the kind of output program that you get for a particular mutation to then back propagate probabilities of how those mutations can happen or change or anything like that?
I've thought about probabilistic programming because it ends up, if I have time, you'll see a bit of tastes of it in the last part of my talk, that I'm really interested in the idea of separating this generator from the distribution, from the random distribution those random calls are coming from. And on the surface, that sounds kind of like probabilistic programming. But I don't know if any of the applications I've had, necessarily back propagation has been a practical thing. So I think I think for a good application, probabilistic programming tools could be another way of providing guidance to the generator, but I haven't, explored that application yet.
Yeah, you need like a much more complex input field, or maybe not. I don't even know. I just threw that out there.
Yeah. So I've
Fair
thought
enough.
of it, but
Fair enough.
But I don't have a good answer yet. Yeah.
Fair enough.
Caroline, can I ask one more question?
Mm-hmm.
Is it important that small changes in the random bits produce small changes in the output, or is it just any sort of change to that bit sequence ought to produce a different output? Are there any properties that we're interested in there?
Yeah, so that's a great question. So initially, Zest, this paper was going to be a lot more complex, and instead of just randomly mutating the bits, we were going to have these this fancier mutation strategy that actually resulted in less destructive mutations on the output. But we found that bigger mutations actually ended up getting you higher program coverage than the fancy small mutations. But there's actually a recent paper called BDivFuzz, which introduces a difference between structural and data mutations that evaluates against Zest and the next thing I'm going to talk about, RLCheck, and finds that you can you can get different notions of input diversity by separating out big mutations and small mutations. So happy to point you to that. But yeah, we've looked at it. Sometimes for bug finding, more destructive mutations is better to some extent, which is counterintuitive. But that's kind of which is a thing I'm interested in exploring as well. Why is that? I guess I don't know if that answers the question.
Thanks.
Yeah. So the neat thing about Zest is that it was because we were conducting these high level structured mutations via the generator, even though, as I said, sometimes they can take quite big jumps between the input you mutate and the input you get. We're still able to find quite complex semantic bugs. For instance, regardless of your feelings about JavaScript, this is an input, a JavaScript input Zest generated, and it's not complete garbage in the sense that it doesn't, cause syntax errors or anything. But when you pass it to the Google Closure compiler, you get an exception during the optimization stage, which essentially is because the optimization was trying to get rid of these statements after the var statement. But actually, this input shows a corner case of the JavaScript language of one particular type of statement you can't get rid of after a break statement without ruining the semantics of the program. So it's kind of cool we were able to find such a corner case via this automatic fuzzing process. So the big takeaway from both of these papers is that in order to explore programs more deeply beyond the parser, you really need to bring in more structure-aware mutations that allow you to make jumps through the search space of structured inputs, rather than just relying on eventually getting lucky with byte level mutations. Yeah, so we had a few questions already, so I'm gonna talk briefly about the RLCheck work in this next section, since it kind of touches on some of what we had questions about. And then I'll try to leave a few minutes for questions at the end. So I've talked about this problem before, right? That the problem with generator-based fuzzing is that you need to tune generators to your program under test. Like say you're testing the Maven build system, you need to write a Maven document generator. We might not want to do that. We might instead but we might know that a Maven document is actually an XML document, and we might be a lot happier reusing an XML document generator to test Maven. But in order to reuse a generator to effectively test Maven, it needs to be that generator outputs inputs of the correct type, of the correct that are valid. And although this gen XML function is always going to generate XML documents, the probability of generating a valid Maven file is not that large. So essentially, all you need to know is that a valid Maven file, there are different subsets of possible tags that are allowed at each different node in the XML document. So as the number of nodes in your XML documents grows, you essentially get an inverse exponential probability of generating a valid Maven document, which is not great. We don't like things that are inverse exponentials. So in Zest, we kind of got around this by, instead of just randomly sampling things, we were really controlling these random choices. We weren't taking them randomly, right? That whole randomness was actually this whole parameter mutation controlled in the back end by coverage-guided fuzzing. And in RLCheck, we wanted to take an approach where we could make this more effective by directly controlling the choices in the generator. Meaning, taking something that maybe looks like a more probabilistic programming approach, where that instead of just having a source of randomness here, we would have the distributions of these random operators be such that we return values that maximize the chance of generating a valid input in the end. So if I can summarize in brief, what happens is that the different choices that are good depends on the context of that choice. Meaning that, if you're the child of the project tags in this XML document, there's some set of tags that are allowed to generate a valid document. It's a different set of tags if you're the root node. It's a different set of tags if you're the child of dependencies, which is the child of project. So we're going to have to add some notion of context to this. The notion of context we added here was essentially the sequence of choices that have been taken so far, because that tell you where you are in the generation process. And then essentially we want to condition our choices based on that context. And what we do in our RLCheck is that we have that generator, and instead of taking choices randomly at each choice point, we have this guided choice interface where each choice point is guided by a reinforcement learning agent. And that reinforcement learning agent is being given a high reward if the inputs it generates are unique and valid. It doesn't actually use any deep learning, it's just regular table-based learning. And you don't need to instrument the program under test, which means you can run a lot faster, which means that we were able to generate many more unique valid inputs in the same time frame. So our RLCheck here is the green line. On the y-axis is inputs that are valid that have different paths through the program. And you can see it can generate orders of magnitude more unique valid inputs in the same time frame than QuickCheck, like just regular generator-based fuzzing, or Zest could. And we saw a similar pattern in the other benchmarks, although there's a question as to whether the RL is overfitting. That actually the BDiv fuzz paper I mentioned found that even though you have different paths, maybe the notion of behavioral diversity that we have in this RLCheck reward thing is not really enough. So given I don't have a lot of time left, I'm gonna skip going over most of Autopandas, but the idea of Autopandas is to do the same hack of you have a generator, but this time your generator is of a program you want to synthesize. And again, you control the random choices. And in that case, you control the random choices to try to generate a program that fits the input output examples. I'm happy to chat more about how that fits in with this offline, but this whole idea is that I'm interested in the idea of separating out the distribution of inputs that is sampled from the user-facing generator, which is just generate random inputs in the search space, and we'll figure out a way to tune the distribution to your desired search. So with all that, I'll conclude, right? I talked about how we can bring fuzzing to new bug domains by generalizing the notion of feedback, how mutations are important to actually explore programs more deeply. And I'm interested in this problem of separating distributions from the random looking generator the user sees. Going further, I'm interested in automated some of the annoying aspects of running a fuzzer, as well as applying these kind of fuzzing search algorithms to applications beyond just finding strange inputs in programs under test. So thanks. And I'm happy to take any other questions.
Thank you. That was really interesting. And definitely, I know we're running up on time, but yeah, hopefully there's some folks might be interested to ask questions or hang around and chat a bit.
I have another quick check based question. So another way that quick check modifies input, not from the framework of modifying input, but from the framework of, from the point of view of reducing the length of the input that triggers a bug, which is their shrinking mechanism, right? So taking things out of an existing input is another way to modify an input. Have you explored any of that in what you're doing?
We didn't explore any differences in test case shrinking. So the JQF Java platform, as far as I'm aware, doesn't have any test case shrinking. The AFL coverage guided fuzzing algorithms use a form of kind of delta debugging to try to reduce inputs. But I haven't explored the details of that shrinking personally. Yep.
Quick question from here. So that was a really cool talk. I really enjoyed it. Thank you.
Thanks.
We're kind of working at the moment actually on a tool that seems that we could maybe integrate with this framework. So I was wondering what might be involved. So our tool kind of takes a grammar, and you can think of it as a generator that will generate inputs that pass this grammar. And so one thing that I'm kind of thinking is, we've been wondering how, obviously it can generate all kinds of inputs based on randomness. So what sorts of things would you say would we need to make it, to add to this tool to make it kind of be pluggable into this framework?
So so you have a grammar and you're sampling inputs from the grammar?
Yeah, I mean, it's exactly like your generator that you were showing for XML, except that it would be the XML grammar kind of thing, or maybe if you had a schema on top of that. And it can just generate kind of inputs that satisfy the grammar. So it's essentially a generator of valid documents. But we don't, like, they're currently completely random kind of. And being able to guide them, I was kind of wondering what would we have to do if we wanted to plug it into this framework and experiment with it.
Yeah, so I mean, the precise things of what you do depends on the language. So the Java fuzzer we have allows you to customize the customize the backend of you would just have to find a way to turn that grammar sampler into like a Java generator, and then you would get the coverage guided fuzzing stuff for free. There's in Python, there's my colleague Rohan Bhavishi that I worked on the program synthesis stuff built a framework a while ago for that kind of allows you to plug in different backends into of like a few random selection operators, which would probably work well for a grammar.
Is there a specific tool I should have a look at if we wanted to play around with it, or is it more of a
I would say the most robust one to look at is JQF for Java. In terms of guided generator-based fuzzing, that's the framework that we have. But feel free to shoot me an email. I think it's like C, my last name, either at Microsoft.com or at cs.ubc.ca. And I can point you to all those things.
Can you put your email in the chat?
Yes. Yeah, and I saw your messages. You can.
Right. Yeah, cases where financial contract terms are put into a simulator, and those contract terms could have things that could break the contract, and so looking for those types of issues.
Sure. Yeah, I'm happy to follow up in emails. It'll probably take me a while to understand exactly what the subtleties are there.
Yeah, thanks.
I have another question, which is in the work you were doing, what was your metric of whether something was correct or not, that indeed this was a bug? So for example, in quick check, you're either comparing two implementations of a program or a program with a model of the program. So there's a reference. What was your reference by which you were able to identify that this is not expected behavior? Yeah,
so in C and C++ fuzzing, right, like we really rely on the sanitizers that have some oracles for, buffer overruns or out of memory errors or whatnot. In Java, we were looking at exceptions that weren't declared to be thrown by right, in Java, there are some exceptions that are allowed, and we looked at exceptions. If it threw an exception that wasn't handled, then we considered that to be an error. For the performance fuzzing stuff, it did require some manual analysis and eventually look at the inputs that maximize hit counts for different edges, and me being like, oh yeah, this is the one that has all the hash collisions. So the answer there is not automated.
So I have a question from way back in when you were talking about, I forget the tool name, the sort of general framework for fuzzing, anything that you could describe in terms of these like key value map stuff.
Fuzz factory.
And you mentioned that like you can recover what the coverage guided fuzzers are doing as an instance of this.
Yeah.
But I guess I was thinking more generally, like what thoughts you have on like the appropriate way to come up with one of those mappings, because it occurred to me, even for the purported goal of the coverage guided fuzzers, the place they ended up in terms of the buckets and the hash tables and all of this was very much like performance driven. I was trying to think like what guidelines would you take to, in deciding what feedback mechanism I want for a particular fuzzing task.
Yeah.
Like what should I do if I didn't already know that someone else had implemented this thing? Great.
Yeah, it's a good question, right? I guess the way you do it nowadays is you look at what did people do for similar things, right? And you try those out and you see how they work in the search. I realize that's not a very satisfying answer. I'm sure that's how they came up with like the bucketing stuff, right? Like AFL, it's kind of funny that you have all these academic papers that, including my own, right, that talk about like, oh yes, there's this coverage guide fuzzing algorithm, it's neat and stuff. And if you read the white paper for AFL, it starts with like AFL is a collection of hacks found to work in practice, right? So I can't deny like there's kind of weird magic to these large search algorithms that, you know, part of it can only, you can only figure out really what's happening empirically. Then, yeah, so then I guess it's like, if you can think of an objective in terms of a monotonic increase of this will lead to my objective, then you kind of know what to do. That's kind of the whole issue though, right? Is like, what is it a monotonic increase of? And I don't know if there's a general way of figuring that out, but a lot of the, like, if you care about multiple different, monotonic is larger than you think, right? So like if you care of like multiple different values for this variable, then you could consider that like my key is like that variable, and then the values is like, oh, you got different values in this set. And as you're increasing the size of seen values, then that's also good, right? Like, oh, I'm seeing if I take this, if I see a new value, then it increases the set of values I've seen. So it's good. So it doesn't necessarily need to just be a number. Yeah, I guess that's not a satisfying answer, but
I guess just musing, maybe this is a place where we should go look at the machine learning world and figure out how they've sort of expanded the scope of things that they optimize.
Yeah, there's reward construction. Yeah, the lab I'm here at MSR New York has a lot of RL people, so I know more about RL than I did when I first created RLCheck, but that's a whole, yeah. So I've talked to a few people about, do those things map to software testing or not? And I guess if we had the answer, we would have a pretty cool innovation.
Can I ask a software lifetime question, which is we typically don't do testing just once, right? We might we might repeat it. Certainly with regression testing, you're doing it over and over again. Does that play any role in any of this? I mean, I don't know, is that just an orthogonal thing that also happens along with this, or is there some integration of those two ideas?
Like, it's not orthogonal. I can't necessarily say that it's something that, you know, that some of these works I've thought a bit about, but I don't know whether I've answered the question. So like in RLCheck, the part of the reason we were thinking about something that didn't require instrumentation is because we wanted to see, can we generate many valid inputs in like 5 minutes? So that it could be something you could run in more of a quick check like time frame, rather than the fuzzing runs, which run for like hours and hours, right? So in that case, you can't like go get a coffee, you know, that's a like, go get lunch or go sleep, right? Also in the fuzz factory, we actually did build a specialized fuzzer, which was trying to target diffs. So if you had like a diff between two versions of a program, then, you know, the keys are locations in the program that have been marked as changed, and then, you know, you keep track of the coverage of those new program locations. But like it didn't work great. Like so I think building a fuzzer that actually works more in an incremental manner has not really been done. And part of that comes from like the only thing you have essentially is restart with inputs you already generated. So it's kind of a difference between these genetic algorithms and some of the AI and reinforcement learning stuff, where in reinforcement learning, you explicitly learn a policy to like search a space, and then you can reuse that policy. Whereas in this genetic algorithm, it's kind of like, well, in the process of doing mutations, I found interesting inputs, but how can I transplant that knowledge to, you know, now fuzz the next edition of my program? Hasn't been fully answered.
Have you tried to look at cases where you're doing a chain so that you have one program with inputs that produces outputs to another program?
Have I looked at that?
I mean, you can break it down by doing it individually, but there might be.
Yeah, you can kind of consider that, like you could consider that the generator-based fuzzing stuff, you're kind of doing that because you're kind of fuzzing the generator, and then the output of the generator is going into the program.
I mean, also the separation you said about the input checking versus core logic is a kind of a chain also, like.
Yeah, so there's a bit of it. So yeah, so that's the place where we would have like the most chain is in that Zest work, where we not only did this generator thing, but we actually had two separate. So this is another form of generalizing feedback that I didn't get into details in the talk, but instead of just looking at increased branch coverage overall, we had like, we counted increased branch coverage by valid inputs, which you can kind of, we looked at, the coverage achieved by inputs that bail out in the first part of the chain versus the coverage achieved by inputs that bail out in the second part of a chain. Because a valid input might cover a branch that only invalid inputs have covered, and that might still be interesting. So you could extend that to, different stages.
Yeah.
But at some point, like, depending on how you're generating inputs to the first thing, I think at some point you see like the number of inputs that are getting through to the next elements in the chain tend to be lower and lower if your input generator is not very good at generating valid inputs that go through the whole chain.
Yeah, I was thinking of situations where you've got a system of piping so that you have a network of processes.
Yep.
You can't necessarily inject the pragmas in the pipes that you would in a compiler.
Yeah. Yeah. Yeah, that's interesting. It kind of reminds me also of, I think there's been some work on fuzzing like stateful protocol, like, if you're fuzzing a protocol where,
right.
I send this thing, then you send me this thing, then I send you that thing. I'm not totally up to date with the most, I think I've seen papers with, stateful fuzzing in the title. I don't know how well they do at that. It was initially an application we were thinking of in Fuzz Factory, but the way that benchmark evaluation goes, it didn't make it in the end. But yeah, so like stateful protocols are kind of another instance of, I need different forms of feedback to say like, no, I'm interested in this because now it's happening at, the second element of my chain, so.
Yeah, it seemed like that would apply to in detection of injection attacks.
Yeah.
Well, very interesting.
Yeah.
You're going to are you going to be in Victoria or Vancouver?
Vancouver.
There's a Vicky Lemieux who's in Victoria. I thought for a minute that you were related to her, but
no, there are other Lemieux I'm related to at UBC, but not Victoria Lemieux. Yeah.
Well, it's always nice to have a name with the best in it.
It is, yeah. It is in the US. People are like, "Oh, what an uncommon name," but actually, it's quite a common name in Quebec. So
can I give you a little interesting piece of trivia? If you might remember from the early 90s, that Digital Equipment Corporation put out the Alpha AXP processor. The X was there purely because the marketing people said it's better for marketing. it didn't stand for anything.
In French, it's just, I don't know why it's there. It's just because we decided we spell words in this way and we're not going to reform the spelling system.
Well, that's the plural.
Yeah, in Muir, it's not, I guess, I don't know if it's, it is plural in some cases, but in Muir, maybe in my last name originally it is, but in the best, I don't think it's plural.
Right.
Yeah.
That's true.
Yeah. French grammar and spelling is
well, it's the extra version for sure.
Yeah.
Well, I really appreciated that, Caroline.
Thanks.
All right, well, yeah, thank you very much. And I guess, Richard, I don't know how we usually wind these down, but